given this cubic, and then we're told that the function has equals 0 equals distinct roots alpha, beta, and then the third root is actually in terms of alpha and beta. I mean, this would normally be our gamma. We're asked to solve completely the equation. So remember your formulae, your summation formulae for roots. We've got the sum of all the roots is going to be minus b over a, where we have a as just equal to 1, then b is minus 8, c is p, and d is then going to be minus 24. So I'll come back to that in a minute. In fact, no, oh, well, let's just write the others down. So the sum of the pairs is then c over a, and the sum of the triples is minus d over a. Those are ones to just learn the general, the truth of quartics and quadratics as well. So what we have here is that alpha plus beta plus alpha plus 12 over alpha minus beta, that's the sum of these three. That must equal minus b over a, so that will be 8 over 1, or just 8. The betas cancel, which gives us 2 alpha plus 12 over alpha equals 8. And this is actually a hidden quadratic, so we can times through by alpha, 2 alpha squared minus 8 alpha plus 12 equals 0. Divide through by 2. And if you try and factorize this, you'll see that it doesn't. You could try 1 and 6 and 2 and 3, but they both have to be negative to get the minus 4 here. So at this point, you can either use a quadratic formula, or you can, it's actually in quite a nice form to complete the square. So that's what I did when I did this question. So alpha minus 2, sometimes it's just easier. I know you might just stick it in your calculator, but alpha minus 2 all squared minus 4 plus 6 equals 0. So alpha minus 2 all squared is actually going to equal minus 2. We've got complex roots here. So that means alpha minus 2 is going to be plus or minus the square root of 2i. Because I'm square rooting minus 2, that's the same as root 2 times root minus 1, which is root 2i. Just remember, when you take the square root, we need the plus and minus as well. So alpha is 2 plus or minus root 2i. Remember, if we get one complex root, then the complex conjugate is also a root. Now, don't get hung up on whether beta is one of these roots or whether it's this one here. Okay, which one's real, which one's not. Actually, it's not going to matter. Let's just go back to the summation. So we know that when we add them, we got 2 plus root 2i and 2 minus root 2i as two of my roots. And then I've got my third root, which I'm just going to call gamma for the moment. I know that is equal to 8. They cancel. 4 plus gamma is 8, so gamma is equal to 4. And therefore we've got our roots. Roots are 4, 2 plus root 2i, 2 minus root 2i. Brilliant. When I did this question originally, I did start messing about with these, and it's just bad idea. It's not needed at all. It's this simple. Once you've got two of the roots, just put it back in and get the third. Hence, find the value of p. So I wrote down all the summation formula at the start. Actually, we've used that one. Okay, for p, we're going to need to use this one here. So now I can say, right, let's do the sum of the pairs. It doesn't matter about these. Let's just pair them up and multiply them. So 4 times 2 plus root 2i plus 4 times 2 minus root 2i plus 2 plus root 2i 2 minus root 2i. That is going to equal c over a, so that's just p. that's how we can calculate p. Just do this little calculation. So 8 plus 4 root 2i plus 8 minus 4 root 2i. They're going to cancel. Plus 4. This is a difference of two squares going on here, so I'm going to get a minus 2 root 2i and a plus 2 root 2i, so I can ignore that. But I am going to get minus 2 times I squared, which is going to give me another plus 2. And therefore p is 16 plus 6 is 22. Nice question. Well done.